Exciting. Okay, so I'm just gonna wait for a sound check just in case people can't hear me. And then I'll get started in like a couple of minutes, I guess. Oh, nice. Okay, so sound check's good, then I will just wait until it's 3 and then I'll start. Okay, so I'll get started. Today I'm going to be covering the second part of the 1081 revision seminar. If you haven't already, you should go check out yesterday's one, which was done by Otto and Isabella. They did the first half, and I'm just going to be covering the remaining 2 chapters of combinatorics and graph theory today. So I'm just going to go and get started. Okay, so our first question here wants us to have 5 points in a plane with integer coordinates, and we need to prove that at least one midpoint of 2 such points has integer coordinates. So essentially, just think of like normal Cartesian plane, right? But we have 5 points in here where each point, let's call them just x, y for simplicity, right? Each point has coordinates that are integers. So essentially, they would be 5 random points anywhere here, and we're looking at any midpoint between any of the 2 points, and we need to show that at least one of these such midpoints has integer coordinates as well. Okay, so I wonder what theory we're going to be using here. So we have a bunch of pigeons in cages, right? So this is the pigeonhole principle. Essentially, we'll be using this to do the question. So the simple case of the pigeonhole principle is if we have n plus 1 pigeons sorted across n pigeonholes, then there is going to be at least one pigeonhole with 2 or more pigeons in it. So how this works is assuming that we don't cut the pigeons, because if we cut them in half, then they wouldn't be pigeons anymore, right? Then what would happen is in the worst case scenario, even if each pigeonhole had 1 pigeon in it, there will be 1 extra pigeon left over, and that means that we are going to have that pigeon squashed with another pigeon in a pigeonhole, so there would be at least 1 pigeonhole with 2 or more pigeons in it. If not every pigeonhole has a pigeon in it, then that means that there has to be a bunch up somewhere. So there is going to be at least 1 pigeonhole with 2 or more pigeons, no matter how you spread it. The generalized form of it is now spreading to n pigeons and k pigeonholes. So it's sort of like a similar idea as before, right? In the worst case scenario, if you were to distribute all of the pigeons evenly, then you would have the n over k in each of them, right? But then you would have some sort of remainder, and those remainders are going to be spread out throughout the pigeonholes as well, which is why we need to do the ceiling function to bring it up from the dividing up to the next pigeon in that pigeonhole. So with n pigeons and k pigeonholes, there is going to be at least 1 pigeonhole with the ceiling function of n over k or more pigeons in it. So we will be using the pigeonhole principle to do this question. Essentially, the idea behind this is because we know that the points are of integer coordinates, then the midpoint can be found by using the midpoint formula here. So if we want to have this midpoint to also have integer coordinates, then that means that it has to be the a plus c and the b plus d, both of them have to be even so that they will be divisible by 2. So let's just consider this separately, and we will consider this separately. So we need a plus c to be even, and we need b plus d to be even. In order for that to happen, we need a and c to be the same parity. And we also need B and D to be the same parity. Note that A and B do not have to be the same parity. It just has to be A and C are matching, and then B and D are matching. That way we can get an even sum, which is going to be divisible by 2. Okay, so obviously integers are either even or odd, right? So since there are 2 points in each of the coordinates, it means that we will have 4 possibilities for parities here, right? So it's either odd, odd, even, even, or odd, even. So of those 5 points, right, these are effectively our pigeonholes. We have 4 of them because these are the only ways that the coordinates can be found in, right? So they're either both odd, both even, or one is even and one is odd, right? So if we have 5 distinct points, right, and we have 4 such possibilities for the parity of the coordinates, it means that by the pigeonhole principle, at least one pigeonhole is going to contain at least 2 pigeons in it. So in this scenario, these are our pigeonholes, and the pigeons are just the 5 points that we have here. So there would be 2 points that have the same type of parity. If there are at least 2 points that have the same type of parity, it means that we will have the desired points that allow us to satisfy this being an integer for both of the coordinates. So that will make it so that we have our midpoint with integer coordinates. Okay, so this next question was from last term's final. Essentially, we have somebody who's trying to allocate the $30,000 investment into 4 different asset classes of gold, shares, crypto, and cash. So just a bit of housekeeping, they have actually denoted different letters for each of them. So G is for gold, S is for shares, C is for crypto, and D is for cash because the C has already been taken by crypto. Okay, so also note that the amount in each asset class has to be a multiple of 1,000. So if $4,000 is invested into gold, then G equals to 4. Essentially what that means is that instead of treating it as $30,000, we can just treat it as units of 1,000, right? So if there is $30,000 in total, then that means that we only need to consider having 30 units being spread out among the 4 asset classes. So it makes the calculations a bit easier if we just consider the smaller number of 30. So I'll just be using the number 30 from now on. Okay, so here are the questions that we need to do under this particular context. So we need to first write down the left-hand side of a fully simplified equation that describes this problem if there are no further restrictions. So where the right-hand side is equal to 0, so what we're looking for is an equation that allows us to express all of the information that we were just given in the question without needing to have all of the shares, gold, crypto, cash, gold, and yeah, that kind of stuff in full. So essentially, if we know that we have gold, shares, crypto, and cash, right? They have to sum up to 30,000, or they have to sum up to 30 units of 1,000. So we know that simply this is going to add up to 30, right? Because all of them are going to be together. So if the question requires us to have something to equal to 0 on the right-hand side, then we need to rearrange this equation, and we get this. The input for this question would have been just this part that I'm going to circle because the right-hand side equals to 0 was already given to you. So all you needed to do was just to type out this. Okay, so now we have just came up with the equation of G plus S plus C plus D minus 30 equals to 0. We need to use this response that we just came up with to determine the number of ways in which the allocations can be made. So remember that they're going to be in units of 1,000, so we only need to think about it as splitting the 30 units among the 4 asset classes. So, since it is not possible to have a negative amount of money in any asset class, it means that every asset class, G, S, C, or D, needs to be an integer that is larger than or equal to 0. So you can actually just put 0 in an asset class if you don't want to invest in it, but you can't have negative numbers in any of the asset classes. And of course, they have to be less than 30, but that's not really too important if everything is larger than 0. Okay, so how we are going to approach this is to think about distributing 30 units among 4 different asset classes. This can be done by thinking of the stars and bars principle, which essentially requires us to have 3 dividers between the 4 different asset classes. So 3 dividers split up the 4 asset classes, and we are going to distribute the 30 among these 4 asset classes. So for example, if you wanted to distribute it like this would be a valid distribution using the divider principle, right? So another way you could do it would be, say, 28, 0, 1, and 1, for example, right? So what effectively we have done is we have used the dividers to move among our 30 units and chop it into pieces so that in each section, that gives us the amount of money that we are going to be allocating in each asset class. So if there are 30 units that we want to split, and we have 3 dividers for everything, then the total will become 33, right? Because we have 30 units that we are trying to split, and we have 3 dividers in the middle. So in total, we would be having 33, and we are now needing to choose 3 positions for us to put our dividers in. So you can think of it as like, let's say we had 30 objects, and we just randomly slipped in like 3 bars somewhere, right? Then that would mean that we would have 33 total things that we are trying to arrange, and then we are looking for the 3 positions that we are trying to put the dividers in. So this would be overall 33C3 if there were no restrictions. Okay, the next part, Harold wants at least $3,000 to be invested in each asset class. In how many ways can this be done? So this is our very first restriction, right? We have to have at least 3 units of 1,000 being invested in each asset class. So just like we had before, G plus S plus C plus D equals to 30. Now everybody needs to have at least 3 invested in each asset class. So if there needs to be at least 3 in each asset class, then that means that we should first give every asset class the 3,000 that it needs, and then we can continue with the question like we did with the stars and bars. The reason for this is because we already know that everything has to have 3,000 in it. We can first give them the 3,000, and we can just distribute the remaining amount among the 4 asset classes. So that makes it so that we can once again utilize the larger than or equal to 0 principle. So if we were to first give 3,000 to everyone, remember that we are just working in units of 1,000 here. This is going to give us a new equation that adds up to 18 after we've given 12,000 to each of the 4 asset classes there, right? So after we've given out 12,000, there will be 18,000 that's left to distribute to the remaining on top of the 3,000 that we've already given to each asset class. In that case, then what we're going to do is just to treat this like a normal stars and bars question. So this, right, everything has to be larger than or equal to 0 now, because we've just given 3,000 to each asset class. And so this is just like the stars and bars principle question that we did before. And so this one is going to be 18, which is plus 3 equals to 21. Choose the 3 particular spots that we want to put the dividers in. So it becomes 21, choose 3. Okay, so part D, Harold changes their mind and decides they only want to invest in at most 3 different asset classes. So in how many ways can this be achieved? When I first saw this question, I got a bit confused because he said that he changes their mind and he decides he wants to invest in at most 3 different asset classes. So I wasn't sure if he changed his mind to start like from the beginning or if he just did not want to do what part C said. But it turns out that it's actually meant to be Harold changes his mind, so he starts completely from the beginning. So this is just like completely like fresh. So completely fresh means that we don't need to worry about any consideration at all, and we just start directly from the beginning where we had the 4 asset classes adding up to equal to 30. If he decides to only invest in at most 3 different asset classes, it means that he can invest in 3, 2, or 1 asset classes, right? But he is not able to invest in 4 because it just breaks the rule that he wants, right? So the way we can do this is just to find out the number of ways that we can invest overall, right? Including 1, 2, 3, and 4. And then we subtract off the ones that are invested in 4 asset classes. So the total we've already found from before. So the total which we got from part B was 33 choose 3, right? So if there are no restrictions, then it would be 33 choose 3. And if there are 4 asset classes, essentially another way of rewriting 4 asset classes would be to just make sure that we are investing at least $1,000 into each asset class, right? Because the minimum amount that you can invest into an asset class is 1,000 because they're in units of 1,000. And if we are going to be investing in all 4 asset classes, then everybody needs to have at least $1,000 invested in them. So that makes it so that we have G, S, C, and D going to be larger than or equal to 1. Okay, so if G, S, C, or D has to be larger than or equal to 1, then we can use exactly the same idea that we did for part C, and we can first allocate $1,000 into each asset class. This guarantees that we are going to be investing in each asset class because the minimum amount is 1,000. So this would mean that G minus 1, S minus 1, C minus 1, and D minus 1 have to add up together to equal to $26,000, right? So if that's the case, then we once again will have 3 bars that divide them up. And so this one is going to be 26 plus 3, choosing the 3 possible scenarios of the position where we want to pick the dividers in the middle, right? And that is just going to give us an overall answer of 33 choose 3 minus 29 choose 3. So what we did here was we first took the total and then we subtracted off the 4 asset classes cases. So we have 1, 2, and 3 asset classes that are left over. Okay. Next question. So Hudson is interested in counting the number of solutions of an equation under various conditions. So here is the equation. We have 15 different terms that add up to 105. Now they can be the same number, but they just are all non-negative integers. So what non-negative integers are, essentially it is just 0, 1, 2, 3, and so on. So it could be all 14 are 0 and the last one is 105, or any other split in the middle. Okay, so what do we have to solve here? Well, when no other conditions are imposed, we need to find the total number of solutions. So just looking back at this, right, we have 15 different terms that add up to 105 collectively. And we are trying to find the number of ways that this equation can be satisfied using non-negative integers. So 0, 1, 2, 3, and so on. Okay, so if we have 15 terms that add up to 105, that means that if there are no restrictions, so everybody is just non-negative, let's just say natural numbers to make it easier, then how we would solve this is just like before with the stars and bars principle, right? If we have 15 terms, then to split the 15 terms separately into each other's parts, then we will need actually 14 dividers in the middle. The reason why we need 14 dividers is because imagine if there were only 2, then we will need 1 split. If there were 3, then we'll need 2 splits. So that means the number of dividers is always 1 less than the number of terms that are there. So there are 14 dividers, and essentially we are splitting the 105 stars using the 14 dividers. So overall, this is going to be 105 plus 14. Choose the 14 locations of the dividers. So this is going to give us 119. Choose 14 using the stars and bars principle. Okay, next we need to find the number of solutions in which every term is congruent to 0 mod 8. So in other words, every term is divisible by 8. If every term is divisible by 8, then obviously the sum of the terms has to add up to something that is also divisible by 8, right? So x1 plus x2 and so on. This has to be divisible by 8. Another way of seeing it is because everything is congruent to 0 mod 8, then if you were to add up the sums of everything congruent to 0 mod 8, then it would make it so that 0 plus 0 15 times would still be 0, right? So no matter how you look at it, the sum of these 15 terms would have to be divisible by 8 as long as each term is divisible by 8. Now, if we look at the question conditions, we are given that they sum up to 105. Now that is an issue because if every term were divisible by 8, then the sum should be divisible by 8. But evidently 105 is not divisible by 8. Firstly, because it's odd, and secondly, if you were to divide it, you'll get a remainder, right? That is non-zero. So if that's the case, then that means that there are no solutions that satisfy this particular property. So this would actually have 0 solutions. So the reason for this is if every term is congruent to 0 mod 8, they all have to be divisible by 8, and so the sum of the 15 has to be divisible by 8. Since 105 is not divisible by 8, there are no solutions that satisfy this currently. Okay, so part C sort of saves us because now we have a bit of breathing space here, right? We can have either congruent to 0 mod 8 or it is congruent to 3 mod 8. We are looking for the number of solutions that satisfy this condition now. Okay, so this one's a bit more complicated, but how we think about this is we first look at all of the stuff that are congruent to 3 mod 8. So look at the stuff, numbers that are congruent to 3 mod 8. The reason why we need to deal with these cases first is because if we know the number of numbers that are congruent to 3 mod 8, we can then subtract it off. So we can subtract off the multiples of 3 that are extra, right? And if we subtract all of the remainders of 3 off of the 105, then we should be left with something that is purely divisible by 8, and then we will be able to use the stars and bars property to do it here. So let me go slowly for this one. If we have 105 as our total of the 15, then we know that 3 mod 8 is going to be the ones that have the extra remainder of 3, right? So if we let the number of numbers that are congruent to 3 mod 8, numbers or number of numbers, if we let this number equal to t, so I'm just counting the number of numbers in x1 to x15 that are congruent to 3 mod 8. So we know that because there are only 15 numbers here, then t must be between 15 and 0 inclusive, right? So either none of the things are congruent to 3 mod 8 or all of them are congruent to 3 mod 8. We know that it is impossible for none of them to be congruent to 3 mod 8 because the part B just showed that 105 is not divisible by 8. So we know that it's going to be somewhere in between 0 and 15. So we now just need to figure out the number of numbers that are congruent to 3 mod 8. How we do this is we know that if we were to subtract off the remainders of 3, then we are going to be left with something that is purely divisible by 8. So if we take a closer look at 105, subtract 3t. This is subtracting off all of the possible remainders of the ones that are congruent to 3 mod 8. Because if it is not congruent to 3 mod 8, it has to be congruent to 0 mod 8. This means that if we take all of the numbers that are congruent to 3 mod 8 and we multiply by t, then subtracting that is going to effectively remove all of the remainders from the numbers and give us something that is purely divisible by 8. So we need to see if this is divisible by 8. There are multiple ways you can do this, but I'm just going to cut to the answer, right? You can test using a calculator, or you can see using the mods which values of t satisfy this. And it turns out that the values of t that satisfy this are t equals to 3 and t equals to 11. So if you were to chuck this in a calculator, the first one, when t equals to 3, 105 minus 3t equals to 96, which is a multiple of 8, because this is 8 times 12. So that satisfies this particular property. And the second one is 105 minus 3 times t will equal to 72, which is 8 times 9, when t equals to 11. Now, the only solutions that are in between 0 and 15 that work are t equals to 3 and t equals to 11. If you test out all of the other numbers in there, it will not work. Also, you'll note that the difference between 3 and 11 is 8. So we know that it has to be increasing by 8 each time. So the next solution would be 19, which is not inside this particular domain. Okay, now reiterating the reason for why I need to do this, because I have now something that is purely divisible by 8 after I remove my remainders, that makes it so that I am able to now solve for the clean remainders of only 0, right? So if I chop off the remainders of 3 from each of those terms, it means that every other remaining number in the 15 would be divisible by 8, purely divisible by 8. So that becomes a new stars and bars question, right? So let's deal with this case first. When t equals to 3, right, if t equals to 3, then we will have 96. So in other words, we are recreating an equation that equals to 96 because we have now cut off all of the remainders of 3 that exist. If it is already divisible by 8, then we'll just leave it in peace. But since we've just cut off the remainders of 3, these 15 numbers have to add up to 96. Okay, we know that these numbers have to be divisible by 8, right? So in other words, if we divide everything by 8, we get a new set of numbers that add up to the 12 that they multiply by, right? Because we know that all of the y's in that sequence are multiples of 8. Okay, so we know that z1, z2, and z15, these have to be non-negative integers because y is multiple of 8, including 0. That means if we were to divide by 8, then z just has to be non-negative integer. Okay, so after all of that, right, we've figured out that we find t equals to 3 or t equals to 11 for the number of numbers that are congruent to 3 mod 8, and then we subtract off the extra remainders to give us something that is very clean and very solvable, this thing here, right? Whoops, I drew a line straight through that. Okay, so these add up to 12, and the number of ways that this can be done is just simply the stars and bars that we looked at before, right? So if there are 15 terms here, and so there would be 14 gaps in the middle, so there would be 14 dividers in between each of them. If there are 12 units that we want to spread over each of the 14 dividers, then that means that there would be a total of this amount of things that we need to arrange, and we are looking for the 14 positions that we can put the dividers in. So this is purely just to put the dividers in right now. Okay, the next thing that we need to do though is we need to pick which ones were the ones that were congruent to 3 mod 8, right? So I could have picked x1, x2, and x15 to be the ones that are congruent to 3 mod 8, or I could have picked x1, x2, and x3, and so on, right? So now we need to multiply by the number of ways that we can pick the numbers that are congruent to 3 mod 8. So the way we can do that is because we have 15 numbers, then all we need to do is just multiply by 15, choose 3 for this particular case, right? Because we have 3 numbers that are congruent to 3 mod 8, and so if we are looking for the numbers like this, then there would be 14 dividers, right? We're splitting 12, 14 dividers, 14 spaces, and then 15 numbers. We choose 3 of them to satisfy the 3 mod 8 condition. So for the first case, let me just rub this out and write it out neatly. Okay, for this first case, we are going to have 26 choose 14 times by 15 choose 3. So 26 was just the 12 plus 14, so 12 that we are splitting, and the 14 dividers in between the numbers. Okay, now using the exact same idea, right? Let me just rub this one out. If we were to rewrite this, now this becomes 72, right? because after we subtract off all of the extra remainders of 3, we are left with something that is purely going to be divisible by 8. So we can chop this into the z1 plus z2 and so on equals to 9, because 72 divided by 8 is equal to 9. So now what we are doing is we are splitting these 9 units across the 15 numbers that we have here. So using the same stars and bars principle as before, we would have 9 plus the 14 dividers in between them. So let me just draw them in. And we would be choosing the 14 positions for the stars and bars to go into. So here would be the dividers, and then multiply. Because we have now 11 numbers that are congruent to 3 mod 8, then we would just need to multiply by 15, choose 11 to figure out the number of ways that we can choose those 11 numbers. Okay, so combining the 9 plus 14, this one becomes 23. Oh, that did not rub out. There would be 23 here, and so the final answer would be taking these two and adding them together, because those two are mutually exclusive events, right? So adding them together gives us the total number of ways that we can have solutions to adding up the 15 terms to equal 105, where they are either all congruent to 0 mod 8 or congruent to 3 mod 8. Okay. Next question. So we have 26 uppercase letters of the English alphabet. How many of these are words that we can make using 23 letters contain this subword QuickTime twice? So an example of such a word is this, right? So you can see that this has 23 letters if you count, because QuickTime should have 9 letters in it. This is very useful for later. So if there are 9 letters in QuickTime, then there should be 18 letters that are purely devoted to just having QuickTime alone, and then there would be 5 letters around it. So 1, 2, 3, 4, and 5 letters that are left over. Okay, so how many 23 letters contain the subword QuickTime twice? The way we do this is we treat QuickTime as a package by itself. So we treat this thing as one unit, a package by itself, because we know that the letters in QuickTime can't be scrambled and they have to be moved in blocks with each other. So if they're going to be moved in blocks with each other, then essentially what we have is 1, 2, 3, 4 as one package, 5, 6, and 7 things in total. So if we treated QuickTime as one package by itself, then we would only need to arrange 7 things. Now, how we do this? Well, because these two QuickTimes, they are identical to each other, then what we need to do is just choose out of the 7 possible locations 2 places for the QuickTimes to go. After that, we have 5 letters left over, right? So U, S, O, J, and Z, that would be our 5 letters left over. They can be any letter from the 26 letters in the English alphabet, right? Because there is no other way that we can make QuickTime, because we don't have enough letters and there's no funny things that happen when you tack on letters to the end or to the beginning of anything. So that means that there are 5 letters that are left over, and if there are 5 letters that are left over, where each position can have 26 possible letters, then all we need to do is multiply by 26 to itself 5 times, right? Because each position can have 26 letters in it. So after we choose the 2 locations to put the QuickTime packages in, then we have the 5 letters left over, 26 possibilities for each, and this is our answer. Okay, how many 23 letter words do not contain the subword QuickTime at all? The way we deal with this one is we look at the total number of words, and then we subtract off the ones that contain the subword QuickTime once. Oh, I do not know what happened there. And then we need to add back QuickTime that appear twice. I'll explain this later, so I'll first demonstrate what this is. Okay, so if we do not want QuickTime to appear at all, then we just do this total subtract off the QuickTime that appears once. Now we need to add back the QuickTime because if we were to just subtract the QuickTime once and leave it, we would be subtracting 2 times when the QuickTime appears twice. So what I mean is if we look at the example that they gave us in the question, so I'll just borrow this one here. If we were to look at this one, where QuickTime appears twice. Now, this is already included in the cases where QuickTime appears once, right? Because if it appears twice, then obviously it would appear once. And then it just so happened to be that, let's say if we picked this one as the one where we forced QuickTime to appear, then there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 letters left over. We've already fixed one QuickTime to appear inside our 23-letter word. If there are 14 letters that are left over, then just purely by chance, there could be a possibility that QuickTime could appear again, right? But when we just do straight up QuickTime appear once and a random arrangements, we fail to also account for the cases where we've fixed this QuickTime and by pure luck, this QuickTime has appeared, right? So you see that there are 2 scenarios where this thing can have the QuickTime appearing once. So if that's the case, then that means that subtracting QuickTime appearing once will lead to subtracting these cases twice. That is not good because we would be subtracting more than we should be. So to fix this issue, we only need to just add back the cases where QuickTime appears twice because this issue only occurs when QuickTime appears twice. QuickTime is not able to appear 3 times because the word is just not long enough, and QuickTime, right, cannot be formed using any other way, so it's just 1 or 2. Okay, so how do we deal with this? Well, for QuickTime appearing once, right, if there are 23 letters, and we essentially have just fixed one whole package to QuickTime by itself, then what happens after that is, as we've said before, there would be the 14 letters that are left over, right? So if there are 14 letters left over, then we treat this thing as one package by itself, and we deal with the 14 letters that are left over separately. Okay, so in that case, there would be 15 units that we need to rearrange, and there is only 15 choose 1 that we need to worry about, because the 1 is just of the 15 positions, we just need to pick one position that we put the QuickTime into. So if it is 15 choose 1 to pick QuickTime appearing once, then we subtract this from the total. The total is just the number of 23-letter words with absolutely no restrictions. We know that if every letter has 26 opportunities and there are 23 letters in the word, then it will just be 26 multiplied by itself 23 times, right? Because each letter has 26 opportunities and there are 23 letters in there. Okay, as I've said before, we need to add back the QuickTime twice case, because if we do QuickTime once, then it would subtract off the QuickTime appearing twice case 2 times, because QuickTime could appear here and then randomly appear in the blue, or it could appear in the blue here as fixed and randomly appear in the red. So if this is double counted, then we need to remove this double counting and we have to add back the cases where QuickTime appear twice. This was done in the previous question, so there we have it. So from the previous question, we had 7c2 times 26 to the power of 5, so that's the only thing that I need to put back here, and we have our final answer for the number of 23-letter words that do not contain the subword QuickTime at all. So total minus QuickTime once, and then add back the cases where we are double counting. So this is sort of like inclusion-exclusion principle, right? Because this just makes sure that we do not overlap, and so everything appears only once when we're subtracting it from the total. Okay, the next question requires us to have the set of all n-digit numbers that are formed by the 9 digits that do not include 0. Let a(n) be the number of such numbers, so let a(n) be the number of n-digit numbers that do not have, so they have an odd number, not do not. So they contain an odd number of prime digits. So they would be odd number of prime digits. So the prime digits would be 2, 3, 5, 7, and 9. So there would be 5 of them. And Bn would be the number of such numbers that contain an even number of prime digits. So what I said about do not before was essentially, if it is An, right, and it contains an odd number of prime digits, then they do not have an even number of prime digits, right? So it is either odd prime digits or even number of prime digits. Exclusive, right? Because if you were to have an odd number of prime digits in your n-digit number, then they would not be possible to have an even number of prime digits in that number, because it's either even or odd, right? So we know to do the first question, we need to write Bn in terms of An. How we are going to do this is because we know that they have to have either an odd or an even number of prime digits exclusive, then the sum of An and Bn must be equal to the total number of n-digit numbers that can be formed, right? Because it can only be even number of prime digits or odd number of prime digits. So let's look at the total number of n-digit numbers. This one's pretty simple because if we have n digits where there are 9 possibilities in each of the positions, so this is just look at the number of possibilities. If there are 9 possibilities for each of the positions and there are n digits there, then it'll just be 9 times 9 times by 9, n times, right? So in other words, this would be 9 to the power of n different n-digit numbers that satisfy the n-digit number property, right, just by itself. So we know that the total is 9 to the power of n, and the total consists of An and Bn, right? Because it was either odd number of prime digits or an even number of prime digits. So they must add up to equal to 9 to the power of n. If it adds up to 9 to the power of n, and we need to write Bn in terms of An, then that means that we will just make Bn the subject of the above equation, and we get a final answer of 9 to the power of n minus 8 to the power of n. So remember, this is the total, this is the odd number of prime digits in the n-digit number, and this is the even number of prime digits in the n-digit number. Okay, so using the thing that we just figured out, we should obtain a recurrence relation for An. So we don't need to actually solve the recurrence relation, but we just need to derive the recurrence relation. Okay, so to do the recurrence relation, we just need to consider the n-1 digit numbers before it. Because if we consider the n-1 digits, so let's just write them out like this. If there are n-1 digits here, then the next digit will force this whole thing to end up having n digits, right? So we only need to look at the n-1 digits case, and then the next one makes it so that it becomes n digits. Okay, note that an-1 and bn-1, using a similar idea as we did before, will cover all possible n-1 digit numbers with no overlaps, because it is either an odd number of prime digits or an even number of prime digits exclusive, right? So it's either A or B. Okay, so how many ways can we have the next digit being a prime? Well, there are actually 1, 2, 3, 4, 5 going to be prime, and 1, 2, 3, 4 that are not prime. So essentially what we do is, if we have an-1, right? If we have an-1 and we want to form the anth number, and an, remember, is the number of such numbers that contain an odd number of prime digits, and so this means that we would have to have the next number that is not going to be a prime number. So if it's already odd, then we need to have an extra digit that is not a prime number that allows us to move on to the an and continue having the odd. If we look at the other case that has bn, right? Bn is going to make it so that if we had bn minus 1, then there would be an even number of prime numbers. No, even number of prime digits in the number, right? So if we want to add it on to the next case, then we need to have the next digit being a prime digit. So we just multiply by the number that allows us to work out the next amount. So overall, right, we can write out the recurrence like this. So if it was already odd, then to make it the next odd, we have 5 possibilities, so we need to multiply onto the end of it. And if they're already an even number, they will need to have a prime that is on the front of that one. So then this would give us our equation here. Note that the sum of them would add up to 9 to the power of n minus 1, right? So if it is 9 to the power of n minus 1, then that makes it so that the total subtract an minus 1 gives us bn minus 1. So bn minus 1 can be made in terms of an minus 1. So this recurrence relation can be purely made in terms of a. And if we were to rearrange, we would get something that looks like this. So we've just removed the bn minus 1 by using the fact that the total of an minus 1 and bn minus 1 equals to 9n minus 1. Okay, so this leads us on to the next topic, where we need to be solving for the recurrence relation as follows. So before we do this, let's go through a bit of theory behind recurrence relations. So the general recurrence relation would have this form. An order k recurrence relation essentially just means that if I start from an, it goes down to an minus k, right? So if we look at the one above us, since this starts from an and goes all the way down to an minus 2, then this means that this is going to be an order 2 recurrence relation because k is equal to 2 in this scenario. Also, right, fn equals to 0 means that this is homogeneous, and fn is not equal to 0 means that this is going to be non-homogeneous. So since the right hand side here does not contain any an's, and this is actually non-zero, then that means that this is a non-homogeneous recurrence relation. Okay, it is linear if all of the things are constants in front of it. And so if it is linear, homogeneous, or homogeneous order 1, then an equals to ran minus 1. And then this would be the simple solution for this kind of equation here. Now, if this is order 2, which is the question that we have here, if it is homogeneous though, the right hand side is equal to 0. So how we would solve this is we first look at the coefficients that make up this recurrence relation, right? So we would come up with a characteristic polynomial that is formed by using the coefficients of the recurrence relation here. So this one would be r squared plus pr plus q equals 0. So because this is order 2, then this would make it so that this is actually a quadratic, right? So this is a quadratic in terms of r, and we have the roots of alpha and beta. So depending on what happens with the roots of alpha and beta, we will have different types of general solutions, right? So if alpha and beta are real and non-equal, then this is going to be the general solution. If they are real and equal, then we will have something that is similar, but we multiply by n to the first solution because alpha and beta are actually the same in this scenario. Okay, if alpha and beta are complex conjugates, then that means that we have this as our general solution. Okay, if it is non-homogeneous, then we would first just solve the homogeneous equation, and then we stick a random term that is Pn that allows us to be the particular solution of the non-homogeneous equation that's like we're solving, and so we just add them together. So essentially we first solve it as if it was homogeneous, so we let the right hand side be equal to 0, solve that, get our general solutions, and then find the particular solution and then just add it to the homogeneous solution. So how can we find this particular solution? Well, we can find this particular solution by guessing a general mirror form of the thing on the right hand side. So if it is a constant, then we just guess a constant generally, just like let it be c or something, right? If it's a polynomial, then we just let it be a polynomial of the same degree. If it's an exponential, then we will just do a constant multiplied by the exponential using the same base. And if it's a product of the previous stuff, then we would multiply, like essentially make the general form of a product of corresponding guesses with each other. Okay, if you have something that makes a guess so that it is sharing terms between the homogeneous solution and the particular solution, then we need to multiply n to the Pn until Pn is completely separate from Hn. Separate. Oops. From Hn. So if Pn's guess, right, using these rules that we have here, if Pn's guess has terms that are still matching inside the homogeneous solution, then we just need to keep on multiplying n to Pn until we get something that does not share common terms with the solution in Hn. So I will demonstrate the example here. This is our current recurrence relation, right? And we can see that if we were to extract the coefficients, we can set up a characteristic polynomial like this, right? So r squared minus 6r plus 9 equals to 0. And if you were to solve this, because this is just r minus 3 squared equals to 0, then this would have solutions, the double root of 3 and 3, right? So using the rule that we just had before, where the roots are real and equal to each other, then this would be the general solution of the homogeneous recurrence relation here, right? So we've first assumed that this right hand side is equal to 0, and then we've solved it to get this as our general solution for Hn. Okay, now because this is non-homogeneous, then we need to actually figure out what the particular solution to this is, right? So remember, the particular solution is just something that is a general guess of something that is of the same form as the thing on the right hand side. So this is 5n 3 to the power of n, right? So essentially we can see that this is constructed from a linear term multiplied by an exponential. So what we can do to mirror this function is if we create the general linear function multiplied by 3 to the power of n. So this is the last rule that we had up here. Product of previous, right, is a product of corresponding guesses. So if we have the linear term multiplied by the exponential, then we need to make a general linear term multiplied by the exponential with the same base. So this would be our guess for the particular solution. Our current job is to guess values, right, that satisfy C and D. So we will be solve for C and D that satisfy this particular solution. Okay, so if we note that this is actually d times 3 to the power of n and cn 3 to the power of n, that is an issue because we remember that Pn only works if it does not share terms that are common with Hn, right? So the takeaway from this is essentially you keep on multiplying n to Pn until you get to something that does not match the terms here, right? Because we already have a times 3 to the power of n and b times n to the power of 3n, and that's the exact same thing as here, then what we need to do is we need to multiply our whole solution to make it so that Pn now equals to dn 3n plus cn squared 3n. However, that is still an issue because we can see, well, I can just change color like that, dn 3 to the power of n matches this form, right? So since it's still matching that form, then we need to multiply by another n. So this becomes dn squared and cn to the power of 3. So squared cn to the power of 3, 3 to the power of n. So now this will finally work because our particular solution does not contain any terms that are common to the solution to the homogeneous equation that we had over here. So after we have our guess, we need to solve for C and D, right? So how we do that is to substitute this Pn back in as an minus 1 and an minus 2, and we need to solve this for the values of C and D by equating coefficients. After we substitute it in and we simplify, we should only get one term that looks like this, and the remaining stuff, if they exist, because there are no other terms that exist like this, then they would all be zeros, right? So that means that the coefficients of everything except for the n3 to the power of n terms, everything else would have coefficients equal to 0, except for this, the coefficient is equal to 5. Oh, whoops, that's not a 5. There we go. Okay, so after we substitute our new thing, which we've just figured out is going to be this, right? If we sub it back in and we replace an with pn, then that makes it so that we have this. It looks complicated, but if you treat the 3 to the power of n separately, because they cannot mix with the polynomials, right? You can sort of just like force this to be 3 to the power of n if you divide this by 3. So this becomes 2 times 3 to the power of n. And then this you can divide by 3 squared. So this just becomes 1. And you can force this to become 3 to the power of n. Then essentially you only need to simplify the polynomial part, right? So if you first deal with the 3 to the power of n's first, then you can just simplify the polynomial part, because you know that 3 to the power of n can be cancelled from both sides since it is non-zero, right? After that, if you expand this and simplify it, you can equate the coefficients. So the linear term, the coefficient of that should be 5. Everything else should have a coefficient of 0. So if you have n to the power of 3 terms, n to the power of 2 terms, and constant terms, they should all have coefficients equal to 0. Because the right-hand side does not have anything that has things that are n to the power of 3, n to the power of 2, or constants, right? So the only thing that you should have is the coefficients of the linear terms should be equal to 5. Okay, so we get basically a bunch of equations if we do the simplification. And we can now solve simultaneously for the values of c and d. So c equals to 5 over 6 and d equals to 5 over 2 if you solve these two simultaneous equations. And then once we've found c and d, then we win, because we can just take this and substitute it back into our guess, right? And after we've substituted back into our guess, then we get our particular solution is equal to this. Once we've gotten our particular solution, we can just add it to hn, right? Because remember, the solution to the recurrence relation is hn plus pn. So we can take the pn and add it to here, and we get a final answer for an equal to this. So the first part, which is this part, this comes from the homogeneous solution. So if we let the right-hand side here equal to 0, then this will give us our solution down here. But we also have to deal with this on the right-hand side, right? So the way we deal with non-homogeneous is after we found a homogeneous, then we guess a particular solution that fits the general term of this. So it would be linear multiplied by 3 to the power of n, and then we chuck that back into this, and then we solve for the values of c and d, which turns out to be these two, and then after we're done, we add them together. So just remember that the guesses to your pn have to match this, but you need to multiply by n until you get something that does not have any common terms to do with your homogeneous solution. Okay, so now we are moving on to the graph theory section. So since I'm on time, I'm just going to go and start this. Okay, so here is our current question, right? We have graph G with 4 vertices A, B, C, and D. We are taking the vertices in that order, so this would be the first, second, third, and fourth one. Poor color choice. This graph has adjacency matrix like this. So you'll see that because this matrix is symmetric, like that, then it means that this is not a directed graph, because basically this just looks to literally see if two vertices are adjacent to each other, right? So here, let's just label them A, B, C, D, A, B, C, and D. If two vertices are next to each other, then this number should be non-zero. So essentially, if they are connected by an edge, then this number should be non-zero. This number here just tells you how many edges there are that connect between the 2 points. So, for example, let's take this thing here, C and D, right? If there is a number of 2, it doesn't really matter which way is which because there is no direction here. Then there would be 2 edges that connect C and D. So there'll be 2 different ways of connecting C and D to each other. So these 2 edges would be called parallel edges because they connect the same nodes to each other. Okay, so now let's take a look at our question. Does the graph contain any loops? If so, which vertices have loops incident on them? So let's take a look at our matrix here, right? So just if you did not hear what I just said, the adjacency matrix just tells us that if we have a number in a particular location with aij, then it just looks at the weight of the edge from that vertex I to the j vertex of g. So in other words, it just looks at how many ways you can go from A to A in this scenario. Okay, if it contains any loops, then that means that it should be joining a edge to itself, right? So here, all you need to do is just look at the ones along the diagonal, because if it has a loop, then an edge would be connected to itself. The other ones are irrelevant because these are connecting points to different things, right? So this one here would be connecting B and A, or A and B if it existed. This one would be connecting C and A, or A and C to each other in 2 different ways, right? So here, because we are only looking at the loops, then we only need to consider the main diagonal of our matrix, right? Because the loops only are the edges from one vertex to itself. So something like that, right? So looking at the diagonal here, if the number is non-zero, then that means that there exists an edge from that vertex to itself because it lies on the diagonal. Okay, so these ones are the non-zero ones. So A, B, C, and D. A, B, C, and D. Since those are the non-zero ones, then that means that A will connect to A in 2 ways, and B will connect to B in 2 ways. So essentially, because they are the same point, instead of looking at it like that, it would just be loops, right? And B would just be loops as well. Okay, so actually, since these are 0, then that means that C and D do not have loops, but A and B have loops to themselves because they are non-zero and they are along the diagonal. Does this graph contain any parallel edges? Give all such examples of edges if such edges do exist. So, if you remember from before, parallel edges are essentially a set of edges that coincide at the same vertices. So, if it begins and ends at the same vertices, then that means that we have to have the adjacent matrix having values that are larger than 1, right? Because if it's only equal to 1, then that means that you only have one edge that connects the 2, right? But if the adjacency matrix has the value in that particular element being larger than 1, it means that there are multiple ways of going from B to C or whatever directly, so that makes them parallel edges. So parallel edges would be, like I drew before, something that looks like this, right? So there are 2 different edges that you can traverse on to go from one node to the next. To figure out what edges have parallel edges that satisfy this, right, all you need to do is look for the values that are greater than 1. Because if it is equal to 0, there is no edge that connects those 2 points. And if it is equal to 1, there is only one edge that connects between the 2, right? So parallel edges requires you to have something that looks at least like this, right? You could have more if the numbers were larger. So you just look at the ones in here that are larger than 1. So how many are there? Well, I've gotten them in red here. So 2 would be larger than 1. So all of these possible ones would satisfy the parallel edges condition. So if we labeled them like this, I should have labeled this one actually. A, B, C, D, A, B, C, D. Then in here, parallel edges would connect different ones. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so technically there should be AA as well, so I'll add that in later. But because we don't actually care about the ordering, right, then what ends up happening is that A and B is different to B and A. Wait, not, okay, so they look different to each other, but they're actually the same thing, right? So in the adjacency matrix, they would come up as different element positions, right? But they all describe the same thing because this is not directed. So that makes it so that AB and BA, they are different in theory, right? But because we only care about the parallel edges that run backwards and forwards, there is actually no difference between AB and BA outside of this adjacency matrix. So inside the adjacency matrix, they would actually be in different locations. So BA would be 0. Wait, actually, this is not BA. Oh, okay, so this would be AA. There we go. Okay, so here, right, let's just use AC as an example. A and C would be connected to each other using two different ways. So in here, we have a position for 2 that connects A to C. And here we have a way that goes from C back to A, essentially, right? So that will come up as 2 different locations, but because the edges are not having directions, then that means that we treat AC and CA as the same thing. So we do not need to write this again. Okay, obviously BB and BB would be the same as itself, and then CB, as we said before, would be the same as BC, and DC would be the same as CD. So we only actually, in theory, need to look at 1/2 to determine this, right? Because as long as we find the numbers that are in 1/2 of this matrix, then that gives us enough information to work out the other stuff, because the other half is symmetric to the upper triangle of this matrix. So the parallel edges are just the non-zero entries here, and then we just have AA for this one, AC for this one, BB for this one, BC for this one, and CD for that one. Okay, part C asks us to find the number of walks of length 3 from vertex B to vertex C. So how we do this is we know that walks are essentially just a collection of vertex, edge, vertex, edge, vertex, and so on. So like it's just a sequence of vertex and edges that go from one vertex to another vertex. You can repeat vertices, you can repeat edges, so it's like the most loose definition, right? And if it's got a length of 3, then it means that you must be able to go from B to C after 3 lengths of walking, right? Okay, so there should be 3 edges in between each of them, actually. Vertex, edge, vertex. So 1, 2, and then 3. Okay, great. So how do we figure this out? Well, if we know that the vertex, the matrix M tells us the number of walks from one vertex to another vertex, then all we need to do is we just multiply the matrix M by itself 3 times to give us the number of walks of length 3. So if we take a look at the matrix M, so M equals to 2, 0, 2, 0, 0, 2, 2, 1, 2, 2, 0, 2, 0, 1, 2, 0. This is the matrix M, right? So what matrix M is telling us right now is it is looking at the number of ways that you can go from one vertex to another vertex. So let's say we wanted to go from A to C. Then there would be 2 ways to go from A to C, right? And so that would just be the number of walks of length 1 from A to C. If we were interested in B to C of walk length 1, there would be 2 ways to go from B to C. Now, if we're looking for the number of walks of length 3, then if we were to multiply this matrix by itself 3 times, then it essentially looks at every stage. If I'm at B and I'm wanting to walk to the next one, say there's 2 to go from B to C, right? Then if I multiply by the matrix itself, now it starts to look at from this point C, where can I go to next? If I multiply by itself 3 times, then the numbers in the matrix will give me the number of ways for me to go from one vertex to another using the walk of length 3. So this is the walk of length 1, and then this would be the walk of length 2, and then this would be the walk of length 3. And so on. You can kind of imagine what this pattern is going to be like. So after we do this to the power of 3, we want to look at the vertex B to vertex C. Now, because this doesn't have any direction, it doesn't really matter which number you pick, as long as it corresponds to B and C somewhere. So let's just say we want to pick this one or this one. It doesn't really matter, because going from B to C is the same as going from C to B when there's no direction. So here it tells us that there are 38 length 3 walks to go from B to C. So as I said before, right, we take m. M is the number of walks of length 1 from any vertex to another, right? So if we were to do this to the power of 3, then it gives us the number of walks from one point to another point with length of 3. So if we wanted to go from B to D, then there would be 21 ways that I can do this with a walk of length 3. So this power essentially just incorporates the length of the walk that we want to consider here. So the answers to this would be that there are actually 38 different walks that we can take to go from B to C. Okay. Next question. So here we essentially have a graph with a vertex set that looks like this. So essentially the vertex set is labeled using these two. You can think of this as coordinates, right? So if we are given the numbers, I'm still here. If we are given, say, random numbers, let's say 1 and 2, right? This will give us a graph that has a vertex set that is specified by this being between the first number that I put here and this having the number at the very top. So we know that A can equal to 1, B can equal to 1 or 2. So all of the points that I can make are 1, 1 or 1, 2. So these would be my vertex sets. Note that these are the Cartesian product of the two integer sets, right? So that means that we would have actually all the possibilities of 1, 1, 1, 2, and so on, right? So that's just the vertex set, and that's how it's defined. So if I were to stretch this number up to 2, then A would be in between 1 and 2, and then now we would actually have a new set that we can create. So that would be the overall vertex set and so on. Okay, we have the edge set that looks like this. Essentially, the edge set, this is not very important. This just tells you that this is what the edge set is defined as. So this is the actual part that we need to be interested in here. This gives us the two vertices that are part of this vertex set that we just looked at above, right? So say this was the vertex set V when W and H are equal to 2 each. So if our vertex set is V, we are taking two particular vertices from V and we draw an edge between them if the difference in the W values or the H values equals to 1, but not the other. So they have to be 1, 0, or 0, 1. The reason why this is the case is because they are integers. So the difference between any two coordinate points has to be an integer value, and it is the absolute value. So it cannot be negative, right? That means that none of these two can be bigger than 1, and if both of them were 1, then that would not satisfy the equals to 1. So it has to be that one is 1, right, and the other one has to be 0, or the other way around. So essentially, we draw an edge between any two vertices if the difference directly between any of the numbers here is equal to 1. So it would look something like this. Essentially, we do not do the diagonals, right? So this thing that I'm going to draw in blue is not included as part of the edge set because this has a difference of 1 for the first number and it also has a difference of 1 for the second number. So adding together, that would be equal to 2, which does not satisfy this property, right? So the only numbers that we can, the only vertices that we can connect are the ones with the points that have a difference of only 1. So it has to change by 1. So for example, we'll be using this graph 5, 3. This would be the vertex set of 5, 3. Now, how this works is this is all of the vertices, right, that are generated using the property that A has to be between 5 and 1, and B has to be in between 3 and 1, right? So we have A is 1, 2, 3, 4, and 5, and B can be 1, 2, and 3, right? So that generates us 3 by 15 equals to, oh no, whoops. 3 by 5 equals to 15 vertices that are available in our graph of G53, right? So here, the edges connect only the things that have a difference of 1 with the coordinates, right? So since from this vertex to this vertex, we only have a difference of 1, so this 1 goes to a 2, the 1s are staying the same, right? So we only are able to join the edges together when there is a difference of 1 with any of the values, and it can only be 1 and the other one has to be the same. Essentially, this creates something like a mesh or a grid, and this is kind of neat outcome. Find all the values of W and H for which GWH has an Euler trail or an Euler circuit. So this is slightly modified from last time. So essentially an Euler trail is a trail which covers each edge exactly once. It is a circuit if it starts and ends at exactly the same point. So we need to actually make it so that we go through every single edge once. You are allowed to repeat vertices, but you cannot repeat edges because you can only go through the edges at least once in this scenario. It is a circuit, right, if it starts and ends at exactly the same point. So the circuit would be just the Euler trail that is repeating the vertex that it starts and ends with, but every other vertex is only reached once. Okay, so here, if it covers each edge exactly once, then we need to have exactly 2 vertices with odd degrees, and it is a cycle or a circuit, Euler cycle or circuit, when there are no vertices of odd degrees. So the reasoning behind this is essentially if we want to come up with an Euler trail that goes from some beginning, let's call this the start and let's call this the end, right? If it needs to go from the beginning to the end, let's just make this simple, right? And there would be one exit and one entry. If we wanted to go back, then to go to the finish line again, we will need to have now 3 degree here and 3 degree here. So essentially, if you're going to go to a point and connect to any other point, right? If you're going to start at that point and end up at a final point, let's say like this, right? Then what ends up happening is that the point that you start at and the point that you end at needs to have odd degree. The reason for this is that every other point along the way that is in between the start and the finish, so let's say there's like random points in the middle that it goes through, it would enter this and it would exit that, right? If it enters it again, then it will need to exit it again and so on, right? So that means that the number of entries and the exits must always be equal, and so that means that there has to be an even degree vertex if it is not the beginning or the ending, right? The only case that you can have an odd degree is if you start and or end at it. So the 2 odd degree vertices are the ones that you start at and end at, because you need to not go back to the original start when you finish at the finish line, right? So the start has an odd and the end has an odd degree. Other than that, if you're going to be a cycle or a Euler circuit, then when you go back to where you started from, you would satisfy this equal entry exit rule. So that means that every degree has to have even degree, right? If you had any vertices with even degrees, if you had any vertices with odd degrees, then it is not possible for you to start and end at the same point. Because if it were to start and end at the same point, then every vertex needs to have an even degree. So the key takeaway from this is just even degree, unless it is start slash end. But if it's start equals to end, if they are the same point, then that means that even degree has to be followed. So if we see that something has multiple odd degrees, then we know for certain that it is not possible for it to have an Euler circuit. And if there are more than 2 vertices of odd degrees, then we know that it cannot have an Euler trail because there can only be one start and one end line, right? Okay, so we are now looking for all graphs of GWH, which was just the mesh that we thought of, right? So you can think of it as just a W by H mesh. So we are looking for these that have exactly 2 or no odd degree vertices. So let's take a look at the graph of G53 that we used for our example, like so. What I've done here is I have colored all of the red as the odd degree vertices, and the blue is the even degree vertices. Now remember from before, right? If you have an Euler trail that does not start and end at the same point, it means that you can only have 2 odd degree vertices, right? If you had multiple, then it's not possible to reach them, enter and exit with the same amounts. If you wanted to have a Euler circuit or an Euler cycle, then you will need to have no odd degrees at all, because everything needs to satisfy the equal entry, equal exit property, right? So that means that every degree needs to have even degree. Every vertex needs to have even degree. So every degree has to be even. So it is not possible to have any odd degree vertices here. Okay, so how do we deal with this? Essentially, since the reds are the odd degrees, then we just need to make it so that the mesh that we have only has 2 red circles, or it has no red circles at all. Those are the ones that we're trying to look for right now. So if we have a side length L, right, there will be 2 even nodes and L minus 2 red nodes, right? So if we were to look at any edge, I'll use black so I don't confuse the colors. If we were to have any side here, right, then essentially the 2 corners are going to be the even nodes, and everything that is in between is going to have odd degree, right? The reason for this is because if we look at any particular red node here, it has to connect to something to the left of it, something to the right of it, and something below it. It does not go up because there is nothing beyond the graph, right? So there's nothing here, which means that it has to have degree 3, essentially, right? So this would be a red node. If it's a corner, then of course the corner only connects to 2 things, so the corner pieces are always going to be even degrees. Okay, so here is our issue, right? Because we only allow it so that we can only have 2 red circles, and any side of length L will always have L minus 2 red nodes, right? That have odd degree. So how do we deal with this? If we were to just increase the length, so let's say I extended this further by 1 more out. So this would be 6.1, 6.2, 6.3, and I recolored this, then what ends up happening is that every time I extend it, the number of odd nodes actually increases. This is blue, blue, and red, and this is blue in the middle, right? So we see that we have just spontaneously created this and this into red nodes, right, or odd nodes, and that is not good because we want there to only be 2 nodes. So increasing this is not going to be the answer. Okay, if we are going to make it so that we only have 2 red nodes, then we need to actually reduce this graph, right? So if we now consider generally the graph of GWH, instead of thinking of such a large graph, right? Because as long as the length is some large number, there will be some number of red nodes that will be larger than 2. We need to make it so that there has to be 2 nodes of odd degree by forcing it to have one side of length 2 and the other side of length 3. So the rationale behind this is because if we have something that looks like this, right, everything else is blue except for these 2, right? So the corner pieces are always blue, and the red ones are the only ones that are going to be the odd degree, right? So if we were to stretch this out in any way, then we would be introducing further red nodes along the top edge and the bottom edge. The other case that this would work is if we had it 3 by 2 like this. Because here we have these two being red, and the corner pieces are the even degrees, right? So in this scenario as well, if you were to increase any length, you would be introducing extra odd nodes, right? So these would be the only ones that have actually two red nodes in them. There is no other way that you can get two red nodes other than these two graphs, because if you were to shrink it, the red nodes would disappear. If you were to shrink it this way, then everything would become so that would be even on both sides. Okay. So this one would have an Euler trail if it were to make it so that it would form on this, right? And this would be the other Euler trail that you can form as well. Also, I've just realized that you can actually have something that looks like this as well. This is actually a valid solution. Although this may be trivial, let's say this is G13 and G31. These are actually also valid solutions, because if you think about it, right, the ones on the end, you can start here and you can end here. And if you had something that was vertical as well, then you could also start at any of the red nodes and work your way downwards, right? And this covers every edge exactly once. So this one would work as well. So essentially we would have 4 different solutions, because this would be actually another way of forcing it to have odd degree on the end of the vertices. The reason for this is because now the corner pieces aren't actually corner pieces anymore, because there is nothing that they are connecting to at the bottom. So overall, what we have are the 4 solutions: G23, G32, G13, and G31. So we are literally piggybacking on the idea that 3 will always allow us to form 2 red nodes, and we only can have 2 red nodes because if there are any more or any less amounts, then the number of red nodes will not be equal to 2 anymore. Okay, now if we want to have an Euler circuit, this is the only way that we can have an Euler circuit, because every node needs to have even degree, right? So in this case, if we have the red nodes all completely gone, then we would have everything having a degree of 2. So this one would work as an Euler circuit, because you can start from literally anywhere and traverse all of the edges before you go back to the beginning vertex that you started from. If you were to make it so that this has any larger size, then you would once again be introducing red nodes, which is not good, right? So this would be the only Euler circuit that you can make in this scenario. Okay. Remember that GWH is our kind of like mesh pattern, right? So we are looking for now what values of W and H will make this bipartite. So recall the definition of a bipartite graph. A graph is bipartite if its vertices can be split into 2 sets, each with the property that no element of either set maps to another element of its own set. In other words, if you were to be able to draw the graph, right, every vertex that you draw from one to another, so if you connect a vertex to another, you can essentially think of them as having opposite parity, or it's easier when you do the exam to draw out diagrams using different colors. So every edge that you traverse from one vertex to another vertex needs to lead to a color change. If, however, it is possible for you to get to the same vertex and have 2 different colors that are conflicting, then that means that the graph is not bipartite. If it is possible to split it so that the graph can be split into 2 different colors, where every red thing is connected to blue and every blue thing is connected to one red node or one or more red nodes, then that means that this graph is bipartite. So essentially the way you deal with bipartite questions is to split it into 2 colors, right? As long as 2 vertices are connected by an edge, they have to be opposite colors. If it is some scenario where there is conflicting color for the same vertex, then that means that this is not bipartite. Generally, you would say that this is not bipartite if there is a cycle that can be formed with length 3 or like 5 or like any odd vertex, any odd length for the walk between them cycle. So like this. So like if you took a walk from here, here, and here and end up with a cycle that was of length 3, then that means that it is not possible for the color change to swap from blue to red here, right? So if you have 3, 5, 7, 9 or any other odd length of your cycle, then that means that it is not bipartite. So what you would do when you're trying to prove this question would be you just take random walks around and you just look for walks that end up as cycles, right? And if you're able to form a cycle that has a length that is an odd number, then it means that the graph is not bipartite anymore. Okay, so let's look at the graph of G53, and we can sort each group into color, right? So as I said before, right, if two vertices are connected by an edge, they need to be opposite colors. So we can see here, if we start off with this, let's make this the color blue, right? So if we start off with the vertex on the left with the color blue, then any vertex that is connected to it by an edge needs to be an opposite color, because that is the idea of bipartite, right? It means that every vertex in the blue set is not going to be linked to a vertex in its own blue set, right? So essentially it means that all the blue vertices are not connected by one edge, like with an edge that is just singularly adjacent to it, and all of the red vertices are not connected by an edge that has like a length of 1, right? So that means that we have to be alternating between red and blue. So the way we will deal with this is, if we know that the first one is blue and everything that's touching it has to be red, then we can essentially kind of like expand it outwards so that everything that is touching the color has to be an opposite color, right? So if this one is red, then the ones that it is touching have to be blue. And this satisfies this, so we are good for this one, right? And this has to be blue as well. And we essentially continue this pattern and we spread it outwards so that everything that touches some other color has to be the opposite color. If we run into any conflicting regions for the vertex, so if any vertex has any two colors that are conflicting on that point, then it means that it is not bipartite. So essentially you could think of this as some sort of algorithm, right? You can just basically take a walk from any vertex to another vertex, and essentially you have to be swapping colors between each time. And if it is possible for you to make it so that two colors are conflicting on the same vertex, then it is not bipartite. If it is possible for you to make it so that you can split it into two different colors, then it means that you have proven that it is bipartite. So we can just keep on doing this idea, and essentially we just spread it out so that if it's touching a blue, it has to be red. If it's touching a red, then it has to be blue. So after we fill out the whole mesh with the different colors, right, now we have a nice alternating red and blue grid, right? And we can see here that this graph is indeed bipartite because there is no conflicting area where blues are touching blues or red are touching reds, and also like two colors are fighting for the same vertex, right? So this is perfect split. So the set of all blues do not get connected to each other directly with a path or like an edge of length 1, and the red vertices are not connected to each other with any like walk that is having a length of 1 as well, right? So everything to go from red to red, you'll need to have a cycle. To go from red to red, you would have to have some walk or a cycle, if you're going to go to yourself, that had an even length, right? So if you wanted to go from this point to the other point, then that would have a length of 2. Or if you wanted to go for a cycle, then you would go from here, 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 here. That would give us a length of 4, right? So as long as you're able to go to your own color, that would take an even number of steps. As long as you're able to go to the opposite color, so 1, 2, 3, if you wanted to go to the opposite color, then that would have a length of 3, right? So if it's odd, you would be changing color. If it's even, then you would be on the same color. So that is how you know that something is bipartite. If it is possible for you to make it so that you have an odd length that walks from one vertex of one color that has a vertex of the same color, then you have proven that it is not bipartite. Okay, so that is what we get. And so we can see that this adjacent coloring does not have any adjacent nodes being the same color. And so that makes it so that this graph is bipartite. Now, if you were to think of this idea in extension, right? As long as you were to just continue this pattern forever, then this is actually also still bipartite, right? Because as long as it is red, it will be surrounded by blues, and as long as it is blue, it'd be surrounded by red. So it means that there is no way that it is possible to make it so that two colors are fighting for the same vertex. So that means that G and whatever is always going to be bipartite. So it is going to be bipartite for all values of W and H. Okay, explain briefly why G95 has no Hamiltonian circuit. So just an update on Hamiltonian circuits, right? A path which covers every vertex of the graph exactly once, except for the vertex at both endpoints of the graph, which is covered twice. So essentially you're going for a circuit that just goes through every single vertex. That's basically it. So how we need to show that this does not have a Hamiltonian circuit, if we can show that something is bipartite, then it makes the Hamiltonian circuit proof much more easier, significantly easier, because if it is bipartite, right, then we can utilize the fact that one step needs to lead to a color change. And so if you're going from, say, red to blue to red, right, that would need to have some walk of length 2. So the edges would be 2, and so this would be an even number. Essentially, each time you go from one vertex to another vertex, you need to swap colors, right? Because you're going from red to blue and blue to red. So if you have an even number of edges in between them, then that means that you would end up at the same color. If, however, it is an odd number, so let's extend this to the next one, which is a blue. If you have an odd number of length, so let's say 3, which is odd, then this ends up going from red to blue. So to summarize this, if you have a walk that has a length of even number, you are going to end up at the same color that you started with. If you have a walk that has a length of odd number, then that means that you have to end up at a color that is different, right? So we will be utilizing this property to show that it does not have a Hamiltonian circuit. Okay, so remember very carefully that the Hamiltonian circuit is that it visits the vertex of a graph exactly once, okay? Except for the one that you start and end at, every other vertex has to be visited exactly once. Okay, so let's take a look at the G95 graph here. Right, so it's essentially just a mesh that has 9 values along the horizontal and 5 values along the vertical, right? So if we are going to go for every single vertex at just like exactly once, so we start from here and we go here, 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 and so on, right? If we go through every vertex exactly once, and we have to end up at where we started, then essentially it means that every vertex is traversed once, except for the one at the beginning, which is essentially reached twice, right? Let's use the idea of color switches. So every edge that we travel across, remember, you don't have to go over all of the edges, you just need to go over every vertex once, right? So if you were to have a Hamiltonian circuit that existed over all of the vertices, there are 5 here, 9 here, so there will be 5 times 9 equals to 45 vertices, right? So let's say if we had 2 vertices, there would be one edge that connects those two, and if there were 3 vertices, then there would be 2 edges, 4 vertices, 3 edges, right? So it's always going to be a length of 1 less than the amount, right? So this would actually be 44, but because you are going to end up at the very beginning, we have to add 1 to go back to where we started from, right? That means that we would have 1, 2, 3, 4 if there were 4 vertices, and if there were 45 vertices that we needed to traverse, then that means that we will need to have 45 color switches, because every edge that we go across leads to changing from blue to red, from red to blue, blue to red, and so on, right? So if there are exactly 45 points that we need to cover, and we need to go back to where we started, then there would have to be 45 color switches, because there are 45 points that we're covering. So it'd be just like this, but extended, right? So 1, 2, 3, and then 4 to go back to the beginning. Change that to 45 and you get the idea. Now, the issue with this is that if you had 45 color switches, it is an odd number of color switches, right? And we said from before up here that if you have an odd length walk, then it means that you have to go from R to B to R to B, or from B to R to B to R. That means that you'll end up at a different color. Now, because we know that this is bipartite, this representation is very useful to us because we know that it has to swap color each time you go from one vertex to another vertex, right? If you have a circuit, you must start and end at the same vertex. So you say you started from a blue vertex, you must be ending up at the blue vertex, right? That is not possible because we have an odd number of color switches. If we have an odd number of color switches, we would be starting from blue and we would end up at red eventually, right? So 45 color switches. Or if you started from red, then you would end up at a blue point after 45 color switches. And so it is not possible to end up at where you began because where you started from was blue in this scenario and where you started from was red in this scenario. So essentially that means that you can't end up at where you started from if you're going to traverse through every single vertex exactly once. So no Hamiltonian circuit exists. The reason why this question was significantly easier compared to most other Hamiltonian circuit questions is because we already proven the fact that this graph is bipartite, right? If we have the graph being bipartite, it helps us significantly because we know that every step that we take has to lead to a color change, right? If we did not know that this graph was bipartite, it would be possible for us to get different colors using different types of cycles or different types of paths, right? So because this graph is bipartite, we know for sure that every step that I take is going to swap me from red to blue or blue to red. So that's why I know that if there are 45 color switches, then no Hamiltonian circuit could exist in here. Okay. D. What is the minimum number of edges that can be added to G42 to ensure that it is non-planar? So just a refresher on non-planar, we can use the Kuratowski's theorem, right? So what this says is a graph is isomorphic to a planar graph if and only if none of its subgraphs are isomorphic to K5 or K33. Essentially what Kuratowski's theorem is saying is if there are subgraphs that are isomorphic to these, then if and only if, so it works both backwards and forwards, then it is isomorphic to a non-planar graph. And just a refresher on isomorphism, an isomorphic graph is essentially just two graphs that are the same, right? They look different, but they are in theory the same if you look at the edges that connect the vertices and the degrees in the vertices and everything. So the simplest way you can imagine it is if you were to just drag the points around and the edges were still connected to the vertices. So say I had like this, right? Then you could, let's say I do this, then you could drag this corner at the top all the way down to the very bottom. Okay, this is starting to get a bit confusing, but essentially this was the thing that I had before, and you can kind of like drag that down from here all the way down. So if you were to drag the point down and the rest of the points just kind of like stay the same and the edges stay the same, so you're not breaking or creating anything new, this would be isomorphic. So essentially there exists a bijection from the vertex set on the left and the one on the right, and a bijection from the edge set on the left and to the right. So I'll go over this in more detail later, but essentially what Kuratowski's theorem is saying is that if it is possible to have a subgraph that is isomorphic to K5 or K33, then it is going to be non-planar. Otherwise, it is planar. Okay, so recall that K5 is a graph with 5 vertices, all connected to every other vertex. So essentially, if we have 1, 2, 3, 4, 5, then K5 is just this. Every vertex connected to each other. So it looks like a really nice star inside a pentagon like that. K3 is the bipartite graph that essentially connects the yellow points to the green points, right? So we can see that if we had the red points up here and the blue points down there, all the red points are connected to all of the blue points like that. So from one red point, you're able to go to any other blue point, and from a blue point, you're able to go from any blue point to any other red point. So that's what K33 is. If it is possible to make a subgraph inside this mesh that is isomorphic to either K5, which is this, or K33, then we can make it non-planar. So we want to add edges to G42 to try to make it so that we can use Kuratowski's theorem to make it so that we have K5 or K33 appear as a subgraph. So this is what the G42 looks like. So this is just the grid or the mesh that we've seen before, where there are 4 along here and there's 2 along the vertical. We want to make a subgraph that is either K5 or K33. So let's look for K5. Remember that K5 is essentially 5 points that are all connected to each other. A defining feature of K5 is that there are 5 vertices. So since there are 8 here, we only need 5, right? So we just pick the ones that give us the easiest way to make it. And so there are 5 vertices that each have a degree of 4. Every single vertex is connected to every other vertex. So that means that every vertex here has to have a degree of 4 because you can't connect to yourself. So if we look at what we have here, currently we need to make 5 nodes each have degree 4, right? Because we just need to have a subgraph. At least one subgraph of this needs to have K5 to be forced in here. So we need to keep adding edges until we can make it so that we have 5 nodes, and only those 5 nodes each have degree 4 that are connected to each other. So if we take the easiest way of doing that, let's take a look at these nodes here. These nodes here are the ones in red. Currently, they have degree 3, right? So the way we can make them have degree 4 is we need to add edges to this, right? So we also need to have 5 vertices. So let's just pick a random one without loss of generality, just like that, right? This one is degree 2 and everything else has degree 3. So essentially, I need to add it so that every single vertex has degree 4. How this is going to work is if I were to at least add edges to each other. So let's say I wanted to add edges here, here, and here. That would make it so that now everything is connected with degree 4, right? Wait, this is not degree 4, it's already there. I would have to have at least this amount because I want to extend it so that they are all connected to each other and they have to have at least a degree of 4, because if it's a subgraph of K5, you need to have at least degree 4 for each node, right? So that would be the simplest way, which means that we will need to be adding a bunch of lines in there. So we would require at least 5 new edges, which seems to be kind of an expensive approach to do this. So let's look at the bipartite representation of G42 and try to force our K33 to appear, because we know that if we wanted to force K55 to appear, it would be a rather expensive process to add at least 5 new edges in, so say something like that, to make it so that this now has degree 4 inside, right? So we'll need to add plenty of edges throughout here to make it so everything is connected to each other, and also make it so that everything has degree 4 at minimum. Okay, if we want to force K33 to appear, we only need to have 6 vertices, because this is enough for us to figure out the K33 scenario. So as long as we're able to connect like this somehow inside, then we get the K33, right? I have a feeling that I didn't do K33 properly. Did I? Ah, there we go. Yes. Okay. So K33, right? If we're able to force K33 to appear, then that means that we can use Kuratowski's theorem and make it so that it is isomorphic to a non-planar graph. So remember that we will be using the bipartite property of K33, and we know that the reds have to be connected to the blues and the reds cannot be connected to each other. Essentially, from any red, you can connect it to all blues, right? And from any blue, you can connect it to all reds, and you make sure that you are not able to go from one red to another red directly, and you're not able to go from one blue to another blue directly. So this red is connected to these 2 blues. We wanted to connect to all of the blues, so we can add an edge in here. Similarly, we want this red to connect to all blues, so we can add an edge like that. This blue is connected to all reds around it. This blue is connected to all the reds. This blue is connected to all the reds, and this red is connected to all of the blues around it. So after adding in the 2 crosses in the diagonals, we have gotten the K33 subgraph that we require. That means that we only need to have 2 edges added in, right? So if we connect 1, 1 and 3, 2 and 1, 2 and 3, 1, then with only two edges, we have already forced K33 to appear. And using Kuratowski's theorem, we know that this means that this is isomorphic to a non-planar graph, right? And this is definitely better than the 5 or more required to force K5 to show up, because remember how we needed to have 5 vertices, all of which needed to have degree at least 4, right? And they all have to be connected to each other, and we drew like a lot of lines in between them. So it means that we significantly have less number of lines needed to be added to make it so that every single graph is connected, every single vertex is connected directly, right? So we can use just two edges and we can just force K33 to appear. So since Kuratowski's theorem is an if and only if, we can be confident that this is the most optimal way, right? Because there is no other way that I can make K33 or K5 appear with just one edge. And so that means that two edges would be the absolute minimum that this is going to give us the required K5 or K33 to show up. So just a few more points on planarity, right? So if we have a simple connected planar graph G that has E edges and V vertices, we have this inequality that may come up in your exam. So it is pretty useful to be aware of this, that the number of edges in that simple connected planar graph has to be less than or equal to 3v minus 6. Now we can extend this if we know that the graph G contains no circuits of length 3, right? So if it contains no circuits of length 3, we know that every single circuit must consist of at least 4 or more, right? That will allow us to have an even better inequality that shrinks this case down to E less than or equal to 2v minus 4. And this can be done, you can tell if there are no circuits of length 3 by looking at the main diagonal for a to the power of 3, for A being the adjacency matrix of G. So essentially like we did before with the matrix M for the very first graph question. Remember how if we do a to the power of 3, that looks at all of the walks from one point to another point that have length of 3, right? If we are looking for circuits that go back to themselves, we just need to look at the diagonal, because the diagonals are all of the points that are connected to themselves. So if we look at the diagonals and we see that there are no circuits of length 3, then we can use this property. Otherwise, it is only able to use this property because this is a specific subset of the inequality at the top. So just remember, you can use the second inequality if it contains no circuits of length 3. So if it look down the a to the power of 3 matrix, right? If the diagonal has no walks to themselves, which is the circuit of length 3, then that means that you can use this inequality. Otherwise, you can only use this one. Okay, so here is a question. We have two graphs below, right? But Edward does not know how to prove that these two graphs are isomorphic. So just remember that isomorphism is essentially the same thing as if you are able to slide around the vertices, right? So let's say if I were to slide this down and the edges were to follow it, then I could get something that looked like, I've run out of space. Let's draw on the side. Oh, I can't do that. Here. So just ignoring the stuff there, but if I were to just slide it down, A2 would still be connected to A1 and A3, and it would still be connected to A5 and A4, right? So it doesn't matter in which position that this graph node is actually in. The graph is always going to be essentially the same idea, right? No matter where I slide this point around. So the connections are the same, like independent of where you are moving the nodes around. So with the numbers, with your lab tests and that kind of stuff, you could have actually dragged for some of them when you have the graphs that are like blue and orange with the arrows. You could have actually just like dragged the points around to see if they were planar or not, or to make the question easier. But if your final exam is on Möbius, you can't have that luxury of dragging around the points anymore. So it's best practice to just draw it out on paper and see what happens if you were to just move the points individually. Okay, so what is an isomorphism? Essentially, an isomorphism is when you have bijections, right, for the vertex set, and you have bijections between the edge set. So what bijections are, if you remember from the sets and like relations, those kind of topic from yesterday, bijections would be the bijection is both injective and surjective, right? So if it's both injective and surjective, it means that it is one-to-one and onto. So there exists a one-to-one correspondence between the vertex set from the beginning and the vertex set on the other graph, right? And it also is surjective. So that means that every single vertex on the right graph has a one-to-one correspondence that can go backwards to the beginning graph. So it goes backwards and forwards for the vertex and the edge sets. To prove that two graphs are isomorphic to each other, all you need to do is just specify what your two okay, before I move on, all you need to do is specify what the vertexes that relate to each other are, and that's good enough. You don't really need to relate the edge sets to each other, because if you match each vertex, so say A1 is B1 or something like that, if you're able to just like match that directly, so if that is equivalent to say B1, for example, if you're able to come up with this vertex mapping, then it means that you have proven that this is isomorphic if it just so happens to be that it actually is the same. Otherwise, if you are unable to do it, then chances are it is not an isomorphism. You can prove that it's not an isomorphism by looking at the things that are invariants, right? So if any of these things are changed, then that means that those two graphs are not the same with each other. Okay, so running through the list of stuff that are invariants, so this is paused, so I'll just go to the end of it. We can see that essentially all of the stuff that are invariants are just the things that do not depend on the relative position of the vertices. So these things, such as the number of vertices, edges, and the sum of degrees, number of degree n vertices, and so on, all of these do not matter where you move the points, right? It doesn't matter if the point is here or if it's like that, right? These were two that are the exact same with each other because you can always move the graph to another location. So think of isomorphism as if you were to just slide the points around and the edges were continued to be attached if they are the same to each other or not. So all of these stuff in this list are independent of the position of the points, which you should be looking at to check if something is actually isomorphic or not. So if we want to show that the graph, right, these two are isomorphic to each other, then we can group vertices that have the same degree and then compare those groups to each other to help us figure out clues as to what the mapping is. So how you would approach this kind of problem is to first try your best to figure out what point maps to what, and then check if that is actually a true mapping, right? So you can use any method that you want up here. You can look at degree, you can look at the grouping of degree, neighbors, and so on, and you can use that grouping to figure out what relates to what first, right? After you have what you suspect relates to what, then you can use the actual check, which is to check what points it is connected to see if those graphs are actually isomorphic to each other. So what is happening over here is that we've got different colors for different degrees of the vertices. So the blue ones are when we have degree 4, the red ones are degree 3, and the green ones are degree 2. So if we do that on both graphs, we see that there are the same number of n degree vertices for each 2, 3, 4, and so we have a feeling that we'll be able to match it up if we look at the neighbors, right? Because it doesn't matter where the points are, you are always going to have the same neighbors. Okay, so let's take a look at this A1, for example, right? We can see that A1 is next to a blue, so I don't actually have green, so I'll just look at blue, green, green, and red. This blue up here is connected to a blue, green, red, and red. So let's go down to these two blues down here. We have this connected to a green, blue, red, green. So this is actually the same as this, right? These two are equivalent to each other because they're both, these two would be the same because they both have two greens connected to each other. Yeah, so one red, one blue, and two greens would make B1 and A1 the same, right? And then here we can see that this blue is connected to one blue, it's connected to one green, and it is connected to both of these reds. So these two would be equivalent to each other. So we can see that A1 is the same as B2 or B1, and A2 is the same as B4. So this would be the edge mapping that goes between both of them. So it's a bijection, which means they are equivalent to each other. You can use the same idea to work out that red is next to blue, blue, and red. And this is next to green, red, and blue. And this one here is next to green, red, blue. And this one is next to blue, blue, red, right? So you can immediately tell that these two are probably going to be the same, and those two are probably going to be the same. So this gives us our edge mapping over here, and you can do the same thing to find the greens that map to each other. Okay, so now that you have these ones, this is what you suspect, right? But you just need to run the check yourself to see if the neighbors are satisfied and everything else is satisfied. If they actually do look like they're the same, you can kind of like move it around to check. Listing the vertexes that match to each other, as long as you list them out, it is fine. So you don't actually need to prove it or anything. You just list out the ones that correspond to each other. So like we said before, these are the edges that map to each other, and these are the vertices that map to each other. If you're able to just map the vertices to each other, that is just good enough, right? If you're convinced that you are able to match it perfectly with a one-to-one correspondence between the left and the right graph, then that means that you have proven that it is an isomorphism, because there is a one-to-one relation or a one-to-one correspondence between the first vertex set and the second vertex set, and that means that all of the edges that are in between them would also be one-to-one matching. So you don't have to prove it. All you need to do is just specify the vertex mapping, and then you're good to go. Of course, if you're unable to do the vertex mapping because something changed, then those two graphs are definitely not isomorphic. So if they are isomorphic, then it means that no matter where the points are, you're always going to have vertices relating to the same vertex. So thus, with this vertex set, we know that they are exactly the same as each other. So the graph A is isomorphic to the graph B on the right. Okay. Next question. So Florence has been trying to analyze the frequency of traffic in their neighborhood. So Florence has constructed the weighted graph G below here. So this question has two parts. The first part is to find the weight of the minimal spanning tree, right? So just a refresh on what a minimal spanning tree is. It is a tree which covers all vertices of a graph and has the lowest total edge weight of all such trees. So essentially, the tree needs to connect all the vertices of the graph together with no loops and no cycles, okay? So to find the weight of the minimal spanning tree, what we use is Kruskal's algorithm. So this is an algorithm that is used for finding a minimal spanning tree of graph G. How this algorithm works is essentially we first look at all of the edges in that graph and we order them by weight. Then we apply a greedy algorithm to take the lowest weighted edge from all of the edges that are currently available to us, right? So each time we would pick an edge that has the lowest weight. Then we include it if it is a new connection to a new vertex, or if it creates a circuit, then we exclude that edge, right? So if it forms a circuit, that means that it would have a point that has already been reached. Then we would exclude that edge and we'll just look on to the next best option, right? Then afterwards, if we have not covered all of the vertices, then we keep on doing this until all of the vertices have been covered, and then this makes it so that we now have a minimal spanning tree. Okay, so let's use this strategy to figure out the minimal spanning tree of this. So we'll use the Kruskal's algorithm on this tree. Now, what we do for Kruskal's algorithm to find minimal spanning tree is for us to first look at all of the edges from the lowest number to the highest number. So here, the lowest number is 1, so we will connect these two, and we would connect these two, right? Because we can see here that taking these two edges introduces new points and it does not introduce any cycles. Now, there are no further edges with length of weight of 1, so we move on to the next number, 2. C2 over here works, 2 over here also works. There is a 2 down here that also works. So that's good, we can take those ones now. Okay, there is no weighting of 3, but there is a weighting of 4. So that weighting of 4 allows us to go and connect these two to each other. Next, we look at the weighting of 5, so we have 5 appear over here. There are no other weightings of 5, and then so we go on to 6. So 6 appears here, here, and just those two. Yes. So now what we do is we take that edge if it does not form a circuit. So if this edge does not form a circuit, then we go ahead and take it. So we will take both of them because none of them form circuits. So just like this. The graph is starting to take shape now because we have now connected all of the points except for A and D, right? Okay, so now let's look at the 7. So 7, 7, 7, 7, and 7. There are lots of points to choose from, right? But we only take the edges that do not create a cycle. So if I were to take the one in blue, which is wrong, this would form a cycle like this, right? That is a bad idea because we don't want to form a cycle, so we do not include this edge. Using the same idea, if we were to take this one, then we would form a cycle of length 3. That is also bad. Oh, wait, no, not that. If we took this one, then we would form a cycle of length 4. And this is also bad because we don't want to form any cycles. So we do not take this 7 down here. Okay, we can in theory take any of the 7s down here because none of them will lead to any cycles. So I just decided to pick this one that goes like this because they are all the same. And then with the remaining 2 7s, right, I can take the one that connects to D, but I can't take the one that connects A and B because that one would break the rule that I'm unable to take cycles. And now I have figured out all of the vertices, right? Every single vertex in this graph is able to be reached. So overall, we would just be looking at the red graph that I've drawn, which makes up my minimal spanning tree. So if I were to roughly draw this on the side, it would look something like this. Like that. Okay, so that's basically what our minimal spanning tree looks like. So every single vertex has been covered and it would have a minimum weighting. So if we want to have a minimum weighting, we can just add up all of the numbers along and then, so it's like 1, 6, 2, 2, 5, 1, 6, 4, 2, 7, 7. And the sum of all of these would give us a total weight of 43. Okay, the final question is to find the shortest path distance from vertex A to vertex Z. To do this, we need to use a different algorithm because this is the shortest path distance from vertex A to vertex Z. To do this, we will need to use Dijkstra's algorithm. So the difference between Dijkstra's algorithm and Kruskal's algorithm is that Dijkstra's algorithm finds the lowest weight path from one vertex to every other in the graph. So Dijkstra's algorithm and Kruskal's algorithm do not need to have the same output graph. The reason for this is because Kruskal's algorithm gives you a minimal weight spanning tree that covers everything and has a minimum total. Dijkstra's algorithm starts from one point and looks at the shortest possible distances to go out from that point. So we would call this a path spanning tree, right? So essentially how we will do this is let v equals to a. So that's like the first vertex that we want to start with, right? And then what we do is we look at all of the paths that go from the set V, that are all of the nodes that are currently visited, and we go and look at the ones that are next to the set V. So currently, if we start off with point A only, then we only look at the ones that are directly adjacent to point A, right? And then afterwards, we pick the one that has the smallest weight. So we pick the path, so from A to that vertex, we add up the whole length, right? And we look at the weight of that, and we take the path if it has the smallest weight. Then, afterwards, we continue to expand that set V, so we add all of the paths to V with all of the points that have already been reached. So it makes sense when I go through the example, but essentially, what we do is we take the points that we have already reached, we look at the points that are next to it, we take the shortest distance, and then after we keep on looking at the shortest distance, expanding, spreading, and then we just expand like that. If not all of the vertices have been covered, then we just go back and return to step 2, and we continue looking for new paths that have the smallest weight and end up connecting all of the vertices. Once all of the vertices are connected in a tree, then Dijkstra's algorithm guarantees that we will have the shortest path from that root vertex A to every other vertex in the tree. So let's apply this to this over here, right? So what we want to do is to first start from point A, because point A is the most important one. The difference between Dijkstra's algorithm and Kruskal's algorithm is that Kruskal's algorithm wants us to pick the shortest total, right? But Dijkstra's algorithm wants us to pick the one that has the shortest overall path from A to any other point in here. So we will need to find the shortest path that goes and connects all of them, right? So A has an extra special emphasis in Dijkstra's algorithm, so we always start with point A when we're looking at the algorithm. Okay, so starting from point A, we now list out all of the edges that can go out from point A. So from point A, we can connect D, E, and B. Those are the only ones that can be reached from A directly, right? Then we pick the shortest edge in here. They are all the same, so it doesn't really matter. I'll just pick B. Once we've picked B, then we scratch it from our list because we no longer need to go back to where we've come from. Once we've reached B, we now look at the new points that it can reach directly. So it can reach BE, right? It can reach E, and we look at the total that it would take. So 7 and 2 means that this whole total path is going to have a length of 9. Also, we can go from B to C because C is a new unlockable point that is adjacent to point B. So BC would have a total of 14. So inside the brackets, you write the total length or the weight of the path that goes from A to that point, right? Through the current vertex that you're analyzing. Okay, so we pick the shortest one. And obviously the shortest one, well, it's just AD for now, right? It also could be AE, but I'll just pick it because why not? You can pick any one when they are the same number because Dijkstra's algorithm and Kruskal's algorithm can give you multiple different answers, right? They are all equivalent to each other in terms of weighting. But if you have like a preference for like alphabetical order, for example, then you'll get a different answer to if I picked AE sometimes. So there's an opportunity for you to get multiple different answers. So you don't have to worry about picking anything. As long as you go for the smallest number, you're guaranteed to be in safe hands. So once we've picked AD, we now list out all of the points that D can connect to. DG has a sum of 15 if we started from A. DE has a sum of 15 if we started from A as well. So it goes ADE, right? Okay, so the lowest number is now AE. So we ended up having to pick it anyway. So it really didn't matter which one we picked in this scenario. Okay, now E is slightly problematic because E is connected to so many things, right? But once you've found E, you can remove it from the edges that are currently under consideration because this is very important. This simplifies your steps significantly. You remove these because you'd already figured out a way that is shortest to go from A to E. So it makes no sense if you wanted to go from A to E using a length of 9, right? If you've already done for 7. So once you've found a vertex that can be reached by a different format, you can scratch it out completely. So now from E, all we need to do is look at E and its new additions. So if we went from A to E to G, that would have a total of 14. A to E to H would have a total of 16. A to E to I, so I'm going in a clockwise order to be systematic, would have a total of 15. And A to E to F would have a total of 13. And then E to C, A to E to C would have a total of 15. Now we look at the smallest number in all of the ones that I currently have, and the smallest path is from A to F through E. So AEF means that I take this one, and that gives me the 13 length. Now, let's look at F. What can F go to? F can go to C and it can go to I. So if F goes to C, F goes to C with a total of 17. F can go to I with a total of 14. Okay, so the smallest number is now 14. So let's just go back and pick BC. And this gets rid of BC like this. Once we've figured out a way to go from B to C, and A to C through B, that is the shortest, then we no longer need to consider the other edges because we know that they are all going to be longer, right? So we can cancel out the ones that end up going to C. So we've figured out all of the A, B, C, D, E, F now. Okay, so now we look at the next shortest edge, and the next shortest one would be EG. So if we connect EG like that, that gives us the 7 in total, that's 14, right? Then we can get rid of this. We can also get rid of DG because we know that we found a cheaper way to go from A to G through E rather than through D, right? So this is useless. Okay, so from point G, what new points can I go to? I can go to J with a total of 15. So if I go A, E, G, J, that is 15. Or I could go to GH with a total of 7, 7, 9, which is 23. or I can go G to K, which is 779, which is also 23. So once again, I'm looking at the smallest numbers here, and I find that Fi with the number of 14 is the smallest number. So I'll go straight from F to I with that 14. Once I've figured out a way to go from F to I for a cheaper length, for A to I is 14, then I can get rid of the E to I because I know that I've already reached I using a cheaper method. So essentially what you do is each time you look at the possible vertices that you can go to next, and you look at the path that is the cheapest to a vertex that you haven't visited before. Once you've gotten to a vertex, you cross off the ones that end up at that vertex, and you start looking for the ones that you haven't reached. So essentially you're spreading out just like you did with the previous part. Okay, so I can reach H in the cheapest way directly. We could have a possibility that goes currently the cheapest way to go to I would be 761, right? So 761, that's 14, and then we have to add 5 on top of it, so that would be 19 in total to go AEFIH, so 14, 19, or I could go to K, so this one would give us 14, and then plus 9 would give us 23, or I can go to Z, and this one would give us 14 plus 2 is 16. Okay, so it is very tantalizing right now because I want to just take this, but we should stick to the algorithm just in case there is some cheaper alternative around the outside, right? So we take the smallest number, that is GJ currently, and if we connect this, then we now remove GJ, and this has a total path of 15. So 771 is 15. Okay, so since J has already been reached, there is no actual other way to go to J, so I don't need to cross off anything. J can now go to K. So JK has a total length of 7716, that is 21. So we pick the smallest numbers here, and the smallest number happens to be IZ equals to 16. So we can actually just stop here now because we know that this total is equal to 16, right? However, for the sakes of completing this question, I've done this ahead of time, so I've figured out that the shortest possible pathing throughout everything is going to be this and this. So you also know that EH is going to be the next smallest number. So you can take EH and then that will connect these two. And then from Z, the cheapest way to go to K is actually from Z directly to K. After you've done this, right, we have now our overall graph. So this is going to take some, I should just make a bigger marker. There we go. That's better. Okay, so now after we've gotten this, essentially what this tree looks like is this. So that's what the tree looks like. And so you'll see that this tree that comes from Dijkstra's algorithm is sort of different to the tree that we got from Kruskal's algorithm, right? Because Kruskal's algorithm is attempting to give us a tree that has total weight being minimal, right? But this one is prioritizing the minimal distance from vertex A. So that's the difference between Dijkstra's algorithm and Kruskal's algorithm. And that concludes the seminar for this term for 1081 for both parts. So if you haven't already and you just came in late, please do check out the yesterday's seminar that was run by Otto and Isabella. They covered the first half and the topics, and I covered the remaining topics today. So yes, thank you guys for attending, and